Question 9. A car at rest in a traffic queue moves forward in a straight line and then comes to rest again. The graph shows the variation with time of its displacement. What is its speed while it's moving? Interpretation of this graph. This is a displacement time graph, and here shows the time in seconds. So from 0 to 50 seconds, the car is at rest. And from 50 to 100 seconds, this is a straight line, which means the car is moving at constant speed, zero acceleration. And from 100 to 140 seconds, this car is at rest. So to answer this question, we need to look at the graph. Which section the graph is moving is from 50 to 100 seconds. The velocity in this blue section is equal to the slope, which means the rise will be 70 minus 30, and the run will be 100 minus 50. So this is the operation, and the answer is B, 0.8 meters per second. Question 10. A car travels along a straight horizontal road. The graph shows the variation of the velocity v of the car with time t for 6 seconds of its journey. The brakes of the car are applied from time equal 1 second to time equal to 4 seconds. How far does the car travel while the brakes are applied? This blue shade line indicates the time the brakes are applied from 1 to 4 seconds. The question how far means distance. In a velocity time graph, the area under the line indicates the distance. Therefore, this yellow shade area is equal to this distance. This is the area of a trapezoid. Here is the formula for the area of a trapezoid. Big base plus small base times height divided by 2. This is the big base. This is the small base. So this is the big base. This is the small base. This is the height. If you still don't see it, you can turn the graph towards you, and then you can see better. This is when you compare this base with this base, this is the largest one. So that's why this is the highest base. This is the smallest one, and the height is the vertical side, not the inclined one, the vertical. Each box corresponds to 1 meters per second. So here we have 22 meters per second. So big base is 22. The size of the smallest base here is up to 8. 8, 9, 10. So this is 8. Plus 8 times height, which is 4, minus 1 is 3, divided by 2. So this area is equal to 45 meters. So the answer is B. Kinematics Worksheet 3. Question 1. A ball is thrown from a point P with an initial velocity u of 12 meters per second at 50 degrees to the horizontal, as illustrated in the figure 2.1. The ball reaches maximum height at Q. A resistance is negligible. Calculate the horizontal component of U and the vertical component. Here is the same drawing, just a little bit larger. In this case, we need to calculate the components of this velocity, the x and y components. To do that, here on the tail of this vector, we are going to set a coordinate. This is y and this is x. And from the tip of this arrow, we are going to project on the x and on the y the corresponding components, which here is ux and here is uy. Using tip to tail vector, I'm going to move this vector here to close the sequence. So as you see, we have tip to tail, and this is the resultant, which is 12 meters per second. Note that I did not duplicate the vertical component, so this no longer exists, and now my triangle is this one. Now we have a right triangle. Now I'm going to use a sine and cosine to calculate the components of this vector. This is the x component, is adjacent to this angle, so I'm using cosine. So cosine of 50 degrees is adjacent over hypotenuse, which is 12. So the horizontal component is 12 times cosine of 50. For the vertical component, because the opposite of the angle on the opposite side, I'm using sine of 50 degrees is the opposite over the hypotenuse, which is 12. My vertical component is 12 sine of 50 degrees. Now I'm using my calculator in degrees to calculate the value or magnitude of those components. In this case, my ux is 50 cosine times 12, which is 7.7 meters per second. And my vertical component is 50 sine times 12, which is 9.19 meters per second. I'm going to write my result using just two significant figures. So the horizontal component is 7.7 meters per second, and the vertical component is 9.2 meters per second. Question 2. Which graph represents the motion of a car that is traveling along a straight road with a uniform increasing speed? So the key sentence for this problem is uniform increasing speed. This is equal to a constant acceleration. Here we have two options with acceleration time graph and two options with displacement time graph. Let me start with displacement. Let me start with the option D. This straight line here, horizontal straight line, indicates that this car is not moving. As the time goes by, the location of the car is the same, so not moving. Is at rest. So definitely D is not an option. Now let's take a look on C. In C, it shows that the car is moving, but how? So this straight line here indicates a constant velocity. This is moving, but with a constant velocity. Constant velocity does not align with uniform increasing speed. That means the speed is increasing, and here velocity or speed. So this one, the speed or velocity is the same. So definitely no. Option B indicates the acceleration is changing over time. And this is not true. This car is moving at constant acceleration. So the answer is A, because it's showing here a straight horizontal line indicates the acceleration is the same as the time goes by. Question number 3. The graph of velocity against time for an object moving in a straight line is shown. Which of the following is the corresponding graph of displacement against time? First, let's study the transition in this graph. So in this section, it seems the object is moving in changing velocity. As the time goes by, the velocity is increasing. So let's call this section A. In this middle section here indicates that the object is moving at constant speed. The velocity is not changing. So let's call this section B. At the section C indicates that the velocity here is getting less and less as the time goes by. So it's kind of decreasing. Before looking the options to determine each one is correct, let me look at each section A, B, and C and draw a distance time graph for each situation. Section A indicates the object is moving at constant acceleration because it's a straight line here. And the velocity is increasing. So the distance time graph that is expected for this section should be something like this, which means that the slope of this graph here is increasing. For the section B, is moving with a constant velocity. In terms of distance time graph, that would be a straight line like this. For the section B, this object is moving at constant velocity, so the distance time graph corresponds to a straight line at which the slope is constant. And the slope is the distance over time, which is velocity or speed. For the section C, the velocity is decreasing over time, so which means will be a curve. However, a curve with a decreasing on the slope. Now we need to find a graph that include all those three variations that correspond to each transition. Option A shows two curves, here and here. However, the curve one is, the slopes are kind of different, and here there is a symmetry. So we should show a symmetry here as well. So A is not correct. Option B indicates that in this interval, the object is not moving. In this interval, the object also is not moving, which is not correct. So here is the original graph. Let's see what we have here, option C. So here we have a curve, and at the middle, we have a straight line. And from the last section, we have also a curve that shows a slope that is getting more flat, which means that in this case is decelerating. Here accelerating, decelerating, and constant speed. So this looks correct, but let me take a look on the last one before select the answer. In this last one indicates here constant speed because the straight line, not a curve. So in this graph, the velocity is changing. Here indicates that it's not changing at constant speed. Here, constant speed, which is correct. And C, also constant speed, which is not true. The velocity is changing, is decreasing. So the best option to answer this question is C. Question 4. When a car driver sees a hazard ahead, she applies the brakes as soon as she can and brings the car to rest. The graph shows how the speed V of the car varies with time after the hazard is seen. Which graph represents the variation with time of the distance S traveled by the car after the hazard has been seen? First, we need to identify which section of this velocity time graph the brakes are applied. So let me divide this graph into sections. So here I have a section A, that the car is moving at constant speed, and here section B, at which indicates the velocity is decreasing over time. So looks like the brakes are being applied right here between T1 and T2. Again, let me draw the distance time graph for each section separately, and then we are going to look the options that best describe what's going on. So at section A, the car is moving at constant speed, which means the corresponded graph, how the graph should look like, should be like a straight line. But here in terms of scale, looks like it's a very small section of time compared with the other one. So keep this in mind. Even though this is not on scale, but this is how we need to look for the beginning, a straight line. For B, we have a deceleration because the velocity is decreasing. So we should be looking a graph with a curve like this. So with these two sections in mind, let's try to find the graph that express those two transitions. So A indicates that from 0 to T1, the car is not moving. And then is at the 0 reference. And from section T1 to T2, the car is in another location, another position, but is still not moving. So this is not correct. B shows the beginning moving at constant speed. We resemble this graph. This is correct. However, the section T1 to T2 indicates that the car is moving at constant velocity, and here is showing that it's changing. So this is not correct. Now let's look what's going on with C. So C, yeah, C is more like what is expected. But let's take a look like this. Yeah, good. But let's take a look if the beginning is a straight line. So here is T1. And you place your ruler. Yes, it's a straight line. So this corresponds to A section, and this corresponds to B section, which is a deceleration here. So that's the correct one. Let me take a look on D. So on D here, yeah, is a straight line. I would say it's correct, but the B section is showing that is accelerating, not decelerating, it's accelerating, because if we get 2 points and find a tangent line, so it's kind of going up, so which means that is accelerating. This one, if you get 2 points here and a tangent line, is going more like level off. So the answer is C. Question number 5. A stone is thrown horizontally from the top of a cliff and falls into the sea sometime later. Air resistance is negligible. Which graph shows how the vertical component, VV, of the velocity of this stone varies with its horizontal component, VH, of velocity as it moves through the air? So I'm going to draw a diagram here that expresses the story. So here is kind of a cliff. This is the base of the cliff. And a stone is thrown horizontally, which means in this direction, from the top of the cliff and falls in the sea. It's fine. So what happened here is that all those 4 graphs is showing the vertical component and the horizontal component of this velocity. So let's see what happened. So here we have the trajectory shape of the stone from the top of the cliff to the sea. And let's kind of draw 4 stages of this fall. And what happened here is this is horizontal, a horizontal component, this one. And the horizontal component is constant, is not affected by acceleration of gravity, because the air resistance is negligible. Now, what happened to the vertical component? The vertical component is seen as a free fall, which means that it starts with 0, VVI here is 0, and as the time goes by, is going to increase with the acceleration of the gravity, 9.81 meters per second square. So VV here is going to 1, 2, 3, is going to change over time. But VH is going to remain constant. So based on this, let's look at which graph actually best represents the variation of VH and VV. I want you to start to look both graphs A and B, because indicates a curve with a increasing slope and decreasing slope. But the situation here is the problem say the air resistance is negligible, which means that the acceleration is constant. So this should not be a curve. A curve for a velocity graph indicates a change of acceleration. That's not the case. So both wrong. Now let's take a look on C and D. So here, let me look at this one. Here indicates that the vertical velocity is constant. And this is not true because the vertical velocity increases over time. So C is also incorrect. Option D is showing that the horizontal velocity is constant. And this is correct because the horizontal velocity is constant during the entire trajectory. It's not affected by the acceleration of gravity. So the answer for this question is D. Question 6. The graph shows how the acceleration of an object moving in a straight line varies with time. So here we have like a bell shape. Which graph shows the variation with time of the velocity of the object? Number 1, this original graph here is kind of symmetrical. So let's kind of divide into two sections. But also I note something. Right here on the top of this curve, something happened, and I'm going to connect to this acceleration right here, to this value of the acceleration. So the velocity time graph that best represents this is, here we have a change of acceleration. Here must have a section with acceleration is constant. And here we have another section of this curve. In these 2 points, I'm going to draw a tangent line, this and this, which indicates the acceleration is increasing and then remains constant for a quick time, and then it starts to decrease. Another way of thinking to determine the acceleration in this section here is decreasing is because if you connect the line with the values here, you can see that it's getting less and less up to 0. So again, you have basically 3 sections here, section A, section B, and section C. Section A, the object is accelerating. Section B is a constant acceleration. And section C is decelerating. So let me start by elimination. So at graph D shows a curve with no transition. So that's kind of a flag that that's not the one. So let's eliminate this. And also indicates like the entire time the object is accelerating. Option B. We should expect something different of the original graph, and this is exactly the same, so I'm not gonna even look at to describe what's going on here because there is no sense, so I eliminate this one too. The biggest flag about option C is this right here. This indicates the velocity is 0, so there is no indication in this graph the velocity is gonna be 0. Here, or is accelerating, or decelerating, or is a constant acceleration. So this is a big no-no. So not waste my time, try to understand this graph. Here is already showing that is wrong. Now, this graph shows a increasing curve, decreasing curve, and right here in the middle, I can kind of find a spot that there is a constant acceleration because there is a straight line right here. The velocity is changing, but at constant rate because acceleration here is constant. So this section, I will say, will be my section B. And here, will be my section A, which makes sense, is accelerating. The velocity is changing, is increasing, but not at the same rate. And after this, we have a curve that is going to is gonna get flat. Right here is the indication. If we connect this, see this, at the end corresponds to this. What that means? Well, that means that right here, acceleration is 0. And what means for this? Means the acceleration is 0 and velocity is constant. So this graph A is correct on each section A, B, and C. That's the right answer.